All right, hello and welcome back. Let's practice a little bit with dealing with vectors in 2 dimensions. And so recall that I had this up at the last video. In 1 dimension, we're able to use a plus and a minus to keep track of the direction part of a vector. In 2 dimensions, we need to employ a coordinate system because plus and minus is no longer sufficient in distinguishing all the different possible directions. And then recall our definition of displacement is final position minus initial position. So here is the problem we're going to look at and see if we can practice some of what we've learned now. Try and push it back further into our memory. So find your displacement in MAD and component form. So remember, MAD is magnitude and direction, so that's some length and it's some angle with respect to the x-axis, standard measurement like we learned in math, right? So remember that if you're dealing with an axis, that this direction is positive measurements for the angle. So this would be an angle of 0, 90 degrees, 180, 270, and back to 0 or 360. Okay, so we're going to, for this particular example, we're going to begin at the origin. So imagine yourself, you're in your car and you start at what we have decided on to be the origin. So that's x equals 0, y equals 0. And you're going to drive north for 3 miles, then you're going to head west for 2 miles, and then south for 5 miles. What was your displacement? Well, first of all, I think we should graphically represent this so we can see what that looks like. So let's take the axes, and the y direction is north. The x direction is east. The negative x direction is west. And the negative y direction is south. All right, so we're starting right here at the origin, and we are driving north for 3 miles. So 1, 2, 3. So we drive up to this point right here, and now we're going to head west for 2 miles. So 1, 2, we're going to head west for 2 miles. Notice how these are tip to tail, right? I'm taking each of these as a separate little displacement, and we'll find our overall displacement, but I can add them all tip to tail graphically, which using, remember, tip to tail, I can add as many vectors as I want. And then the last one, then we're heading south for 5 miles. So we are going to go south 1, 2, 3, 4, 5 miles, so all the way down here. So our total displacement then can be represented as that vector right there. So that's the total displacement, or vector R, resultant vector. So the resultant vector is the addition of these 3 displacements along the coordinate axes. So let's see if we can describe vector R in both component form and in MAD form. So first of all, let's look at the component form of vector R. So vector R is going to be equal to, we need these 3 vectors added together, and we're going to use those unit vectors that I introduced in previous videos so that we can distinguish all of them. And then remember that we only add x's to x's and y's to y's. So we are heading north, that's positive y-axis, for 3 miles. So the first displacement is 3 miles, and that's along the y-hat direction. The next piece of the displacement is 2 miles to the west, and the west is minus x. So that's going to be plus 2 miles along the negative x direction. And then lastly, we're going to go 5 miles along the negative y direction. So this is going to be plus 5 miles, and that's going to be along the minus y direction. So there is our displacement in component form. We're going to simplify it a little bit. So these are both the y direction. I've now taken all of these and placed them only along x and y directions. So we have the total amount along the x direction and the total amount along the y direction. So notice that there's nothing to add to the x direction, so this is going to be 2 miles minus x, or along the negative x direction. And now these two added together, I've got 3 miles in positive y and 5 miles in negative y. That's going to leave me 2 miles in negative y. Okay, this expression for r is exactly the same as the expression above it. Notice I can factor out that minus sign if I would like. I just need to remember, though, that the sign goes with the direction part of the vector, not the magnitude part. Okay, so these two right here are equivalent component forms of the displacement. Component form of displacement. Now what about the MAD form? So remember, the MAD form is how long is this arrow and what angle does it make with respect to the x-axis. So that angle I'll call theta. So MAD form for r is going to be the length of r and the angle it makes with respect to the x-axis. So notice that I have a vector that is along the minus x direction and along the minus y direction. There's only one quadrant where x and y are both negative. So notice each quadrant has a distinct set of conditions for x and y. So in quadrant 1, x is positive and y is positive. In quadrant 2, x is negative and y is positive. In quadrant 3, x is negative and y is negative. And in quadrant 4, x is positive and y is negative. So each one has a distinguished set of criterion for x and y, and so we see we're in the third quadrant, and of course when we drew it tip to tail we see of course we are in the third quadrant. So what I can do is take this little triangle, which I will polka dot right here, okay, and I want to figure out, I know the two legs, the smaller legs of this triangle, and it's a right triangle, so that means I can find everything I need to know about that triangle. So let's take that triangle and let's blow it up right here. So here is the triangle. This is the length r. This is the piece along the x-axis, which we know is 2 miles. And this is the piece along the y-axis, which we know also is 2 miles. So notice that this angle right here, which I'll call phi, is part of theta. How would I get theta if I got phi? Well, I would just add the 180 degrees to phi to have that whole angle theta. And I can do that. I can find phi because I have the trigonometric relationships. I have access to those trigonometric relationships, and I know two sides of the right triangle. So that means I know everything about the right triangle. So I can find the magnitude r as the square root of 2 miles squared plus 2 miles squared. And so then r is going to be equal to 2 miles times the square root of 2 in length. So that's the magnitude part of r. Now we need to find the direction part of r. So first of all, we need to find phi. So phi is going to be the tangent inverse, right? Phi relates the adjacent and opposite side through tangent. So the tangent inverse of opposite over adjacent, so that's going to be 2 miles over 2 miles. And if you work that out, you'll find that's 45 degrees. So then the angle theta is going to be equal to 180 degrees plus phi. So that's going to be equal to 225 degrees. So the vector r then can be described in MAD form as square root of 2 times 2 miles. That's just some number. You can work it out in your calculator. I don't have one right here, at 225 degrees. So now we have the vector r in mad form. So this is the mad form of the vector. And we have vector r in the component form. So there's the forms, and these are equivalent, right? We just factored out the negative sign in front. But again, be careful. Remember that the number with the units is the magnitude part, and any sign with the direction or with the unit vector is going to be the direction part. So there's a nice example of how we can use the unit vectors and add these small displacements in these different directions along these axes to come up with the total displacement. Thank you.